My goal for this video is to understand how the probability generating function allows us to calculate extinction probabilities. It's been a while since we've met, so I wanted to review some basic principles from our last class. And so these basic building blocks is my attempt at providing that summary. So we're going to start with talking about our offspring distribution. We want to remember that every individual in our population is considered to have a random number of offspring, and every individual in every generation has the same probability of having any given number of offspring. So pk is going to represent the probability that the number of offspring, which is a y random variable, equals a value k. And a little bit later we're going to be talking about a sequence of random variables, and this allows us to talk about the number of random offspring from particular individuals during particular generations. So the subscripts in the y sub ni allow us to focus on which generation and which individual we're talking about. But all of those are independent and identically distributed using the same distribution of our original offspring distribution. The key calculation that will allow us to determine extinction probabilities is the probability generating function, and I'm going to summarize that probability generating function often using the initials PGF. So PGF stands for the probability generating function. Just a reminder of where that probability generating function comes from. There's a variable s that's just think of it as a variable, and what we're going to be doing is we're going to be calculating the probability that y equals a specific value times that input raised to the k. And what this allows us to do is this is actually the expected value of that mathematical variable raised to the random variable power. Okay, and what this allows us to do is we'll later use this in our calculations, because we'll have this s is going to be raised to a sum power, and by independence that'll factor and result in powers of our generating function. So just as an expectation of where that's headed. Okay, so our actual branching process, we start with some number of individuals, and then to find the number of individuals in the next generation. So x sub n minus 1 represents the number of initial individuals in a population. Generation n minus 1 allows us to calculate the number of individuals in the nth generation, the next generation, by summing over all of the individuals in our original population and adding up the number of random offspring that each of those individuals have. And so our calculation is going to be based on the fact that we have a sum of independent random variables. Sum of independent random variables. Our next step, or currently our first step, in understanding branching processes is to learn that our expected number of individuals in a given generation, if I look at the expected value or the average value, this behaves like an exponential growth or decay. And the way we're going to do that is we're going to take advantage of conditioning. And so this is a really, really common strategy in stochastic processes, where to calculate the expected value of some random variable, we will actually first find the conditional expectation, and once I have this conditioned expected value, I can then say, well, what's the average of the conditional expectation? And that actually gives me the same expected value. So I can now think about all possible values at the n minus 1 generation and see what that leads to at the next generation. What that means is we're going to say, to calculate the expected value, what we'll actually do is we're going to sum over all possible values. So here we're going to say we're going to go from 0 to infinity, and we're going to say what is the expected value of the conditional expectation. So this means I, let's clarify, I is the value of x sub n minus 1. And so what we'll do is we'll say what's the probability that x sub n minus 1 equals I, and we're going to multiply by the expected value of x sub n conditioned on the knowledge that x sub n minus 1 equals I. And so this is the expected value. I'm taking a probability times the value of the unknown, and here the value of our unknown is the conditional expectation, and we can now calculate this quantity. So what is x sub n? Well, it's the sum of the y's. So let's review that really quick. The expected value of x sub n conditioned on x sub n minus 1 equal I. Maybe I should have called that k. I think that's what the book does. So let's change that to k here. Is the expected value of x sub n given that x sub n minus 1 equals k. Well, this means that we're calculating an expected value. X sub n is the sum of I goes from 1 to the k individuals in my population of y n minus 1 comma I. And this is conditioned on x sub n minus 1 equals k. So what we've done is we've replaced x sub n with its definition in terms of our information, and now conditioned on this value x sub n minus 1 equals k, these number of offspring is actually independent of all of that. And so the expected value for each y is equal to mu, and so I get k times mu, where mu equals the expected value of our random variable y. So now if I replace the conditional expected value by our calculation k times mu, and again let's clarify that the book probably wants us to think of this as k, so we're consistent. We have the sum, k goes from 0 to infinity, of mu times k times the probability that x sub n minus 1 equals k. And if I take the sum of k times the probability that xn equals k, that's the expected value of x sub n minus 1. So what we've shown is the expected value of x sub n equals mu times the expected value of x sub n minus 1, and if I use induction or recursion, I discovered that the expected value of x sub n is mu to the n, that's the exponential part, times the expected value of x sub 0. And this was the goal of this particular step of our analysis. The next step of our analysis is to use this expected value to tell us something about probabilities. And I actually think this is a really clever trick. So what we do is we write down what the expected value means. So the expected value is the sum of the possible value for a random variable times the probability that it takes on that random variable. And for these positive random variables where xn it has to be 0 or a positive number, what I think is clever is what we're going to do is we're going to make the inequality smaller, or this sum gets smaller, by recognizing that k is less than 1. Sorry, k is greater than 1. Let's fix that. For all values that come after 1. Now that seems like a ridiculously simple observation, but what this allows us to do is we are going to be able to say that the expected value of x sub n, which is the sum from 0 to infinity of k times the probability that x sub n equals k equals 0 doesn't show up at all. And so this is less than or equal to the sum k goes from 1 to infinity of the probability that x sub n equals k. And I made the exact same mistake. Remember that inequality was the other direction. K is bigger than 1 or equal to 1. And so this is the probability. The expected value of x sub n is always greater than or equal to the probability that my x sub n is greater than or equal to 1. So if our expected value decays, in other words, if mu is less than 1, this tells me that the expected value of x sub n converges to 0 as n goes to infinity. And this tells me that the probability that x sub n is greater than or equal to 1 also converges to 0. So the probability of extinction has to equal 1. So anytime the mean number of offspring per individual is less than 1, on average, if you can't replace yourself in a branching process, the overall process is guaranteed to go extinct. So here we have another collection of basic information. Our goal is that we want to know, okay, is a population going to extinct when the average is greater than or equal to 1, so the average number of offspring. So let's make some definitions. Here, let's see, we have this script E is just going to be our shorthand notation to talk about the overall population goes extinct. We'll think about the probability that at time n we've reached extinction by time n, and so we'll call that an of k, and the limit of that sequence will be our extinction probability, and all of this is conditioned on the original number of offspring. So if I think about each branch, each sub-branch, because the number of offspring in each sub-branch doesn't depend on any other branches, the probability that I go extinct in k branches is the product of the probability that I go extinct in each branch, and there are k branches, and so I get this power through independence. And so if I if I want to know the value of a sub k, it's simply the probability that one sub-branch goes extinct raised to the k power. And so really all we care about is this probability of extinction given that there's only one individual to start off my branching process. So now we're going to do what's called first step analysis. We're going to think about A, which is the probability of extinction, and we're going to condition this on the first step. And so we're going to do the sum over all possible first steps. So how many offspring we have. K is going to go from 0 to infinity. And we're going to ask, what's the probability, first of all, that at step 1 I have k individuals conditioned on x0 equals 1. So that's the first step. And then we say, okay, given that I've stepped to now have k individuals in the next generation, we need to say, well, what's the probability that I ultimately go extinct if I know that at generation 1 I have k individuals? And since I only have one initial individual, the probability that x1 equals k, x1 is the y random variable, and so this is p sub k. And the probability of extinction, now I have k branches, I get to multiply this by, because of our power of independent branches, a raised to the k power. And so a equals pk, sorry, I missed the sum. Let me fix that. We're going to sum. K is going to go from 0 to infinity, and this is how we calculate A. And this is what we defined earlier as our probability generating function. So this is our amazing fact. The extinction probability solves the equation that value A equals the probability generating function of A. So we just saw that our extinction probability solves the equation A equals phi of A, where phi is the probability generating function for y. The only question is, it might be that this equation has more than one solution, and so we need to find a way of understanding, well, which of all the solutions do I want to consider? Now, because of our way that our probability generating function is defined, phi of 1, which is the sum, as k goes from 0 to infinity, of s, which is 1, to the k, times the probability of k. 1 to the k is always 1, so I get the sum of the probabilities. K goes from 0 to infinity. What we've discovered is that phi of 1 does equal 1. So we found at least one solution. The question is there another solution, and is it possible that A happens to be that other solution? So this particular step in our analysis is going to find a way of calculating A as the limit of a certain sequence. And we're going to do that by thinking about the probability generating function not of y anymore, but of the actual stochastic process of our branching process. So let phi with this parentheses n, and I put it in parentheses because the textbook uses just n. It's not clear if that's supposed to be a power or an nth composition, so I want to make it clear that we're just talking about the probability generating function of the nth generation of individuals. Well, this time we're actually going to do a last step analysis, and so I'm going to do an expected value conditioned on the next to last generation. So we actually did this earlier. We're going to say that the expected value of s raised to the xn, so that's our probability generating function, is going to be the conditional expected value. So we're going to sum over all possibilities of the n minus 1 generation. So this is the probability that x sub n minus 1 equals k. Let's see, we are going to condition, of course, on our starting with only one individual, so I'm just not going to write that because that's how we're defining everything. So it's the probability times the expected value of s to the xn conditioned on knowing that x sub n minus 1 equals k. Sorry about the sloppy lining there. Okay, so let's see. What we're going to do now is the same thing we did earlier. We're going to replace xn with the formula that xn is really a summation. So let's see, we're going to rewrite this. So the sum k goes from 0 to infinity of the probability xn minus 1 equals k times, let's see, the expected value of s raised to a summation going through all of the individuals in that previous generation, and we want to know how many offspring they had. And officially this is now conditioned on x sub n minus 1 equals k, but nothing in the expression that we're finding a condition of, none of this actually depends on that, because k is at this point a constant, so we don't need to worry about this conditional expectation. Well, this s raised to a sum power can be rewritten as a product. Let's do that. This is a summation k 0 to infinity probability xn minus 1 equals k times the product, the expected value of s raised to the y. They all behave the same way, and I get to multiply those because they're independent. So this is raised to the k power. And so this is equal to actually the probability generating function for the n minus 1 generation, and what's taking the role of s is actually the probability generating function of y. So I can see I actually should have done the first step analysis, because what I really wanted to show, the expected value of s to the xn is the sum over all first steps. So let's do k goes from 0 to infinity of our first step probability that x1 equals k times the expected value of s let's see. So I want s to the xn conditioned on x1 equals k. And I'm just thinking about what to do at this point, because what I did earlier, I had a composition, but this is actually the reverse order. I want phi of phi sub n minus 1. And the book goes through this argument that's it's a reversal of summations. So I'm trying to figure out how to explain it in an alternate way. Alright, so here's how it works. What we found is we found this expansion, and in our previous calculation, when I did the last step analysis, I thought about thinking of xn as the summation of offspring from individual I from the n minus 1 generation. And what we're now going to do is we're going to think instead of all of the sub-branches coming off of the first generation. So we're going to think about sub-branch I, and xn is the sum of those. Now, again, by independence, these individual contributions are independent. So what I've done is I've rewritten the probability that x1 equals k. Well, that's a single individual having offspring. These are the probabilities for my y distribution. What I'm now going to think of is this s to the xn is actually going to be s to the offspring from branch 1 times the s to the branch 2 times s to the branch 3. Those are independent. And so I can write this, the expected value of s to the branch, I wish I had a way of some notation, but what it's really going to be is it's going to be equivalent in distribution to s to the xn minus 1 if I had started at time generation 0 with 1, and I multiply those. So the idea is each sub-branch going from 1 to generation n is like going from generation 0 to generation n minus 1. So that's the same number of generations between where I started, except that generation 0 starts with 1 and generation 1 starts with k. And by independence, what we'll do is we'll say, okay, each sub-branch is independent, so I get that to the kth power. Okay, so now we're back to where we wanted to be. This is our quantity that's sitting here in the place of s is phi for the n minus 1 generation of s. Okay. So what I've found is that phi for the nth generation of s is equal to the generating function for y of generating function for n minus 1 of s. And this is now a recursive way of calculating phi sub n. So now we have a way of finding relationships between our probability generating functions for our stochastic process. What I want to show now is that this allows us to calculate A. I'm going to start by pointing out that if I want to know what's the probability that x sub n equals 0, and recall that this is what we defined as A sub n. We start with 1, so it's given that we start with one individual, what's the probability I'm extinct at generation n? If I think about the probability generating function, this is actually the probability generating function for generation n evaluated at 0. Because if I think about the summation of s, so k goes from 0 to infinity, s to the k, probability that x sub n equals k, if I say s equals 0, only the probability that x sub n equals 0 survives in the summation. So what this tells me is that if I want to know the probability of extinction at generation n, this is equal to phi by the recursion of our previous thing, the probability of generation n minus 1, which is equal to phi of generation n minus 2. And so I can calculate a sequence of my probabilities of extinction. Now, at generation 0, the probability of extinction is 0. At generation 1, the probability of extinction is phi of A0, which is phi of 0. If I want the probability of extinction at time 2, this is phi of A1. And so I'm creating a sequence through this function, phi. And what are some things that we know about that function? We learned, well, okay, so at the top of this slide you can see we want to graph two things. We want to graph y equals s. So here's y equals s from 0 to 1, so here's 1. And we also want to graph the phi function. What did we learn? In our previous class we learned that we know it goes through 1. We know it starts above 0. So let's change the color here. It starts above 0 because this is P0. And we have two possibilities. Well, we know that we're increasing and concave up. So one way could be increasing and concave up. And the other way of doing the graph is that we could be increasing concave up and only touch it at 1. So we might be some sort of function that's increasing and touching at 1. Well, what does this sequence recursion say? It says I start at 0 and I see what value the function is. And to find the probability at the next generation, I use that value and I calculate the next value at the function. So here's P0. this new value is P1. I then go to P1 and I repeat the process. Well, I can't see it very well in that picture, so let's go to the other one. At generation 1, the probability is P0. At generation 2, at generation 3, and 4, I just sort of steadily march up the way. And because I'm increasing, I always have to be going up, and I can't ever cross that first root. And so the key fact that we get out of this is that my sequence will always converge, A sub n will always converge to the smallest root of the smallest solution to the equation A equals phi of A. And so this is what allows us to do our calculation. A is the smallest solution to A equals phi of A. Between 0 and 1, maybe equal to 1. Okay. And finally, the last thing that we talked about in class is the only way to get a root less than 1 is if the slope is greater than 1. And that only happens if the mean number of offspring per individual is greater than 1. Alright. Well, I'm not sure that last slide was the clearest, but hopefully that gives you the idea of what we're trying to do. And this is what was covered in the textbook in section, what section was that? 2.4. Alright, hope you guys had a great weekend. See you Tuesday.